The ramp for a building access can be modeled by the function f of x equal 10 minus 1 over 12x, where x is the horizontal run from the building's door, and f of x is the vertical distance from the ground level, both in inches. Sketch the graph of f. What is the slope of the graph, and at what rate is the ramp changing? Now, for buildings access, for accessibility, there are legal requirements how steep the ramp must be. And so in this case, if the ramp is modeled by this function, then we recognize that the slope in this case is negative 1 over 12. And also the initial value is 10. And so the ramps start with 10 inches above the ground level. The slope is negative 1 over 12, which is rise over run. But in this case, it is more like falls over run. What that means is that for every 12 run, horizontal distance, for every 12 units, for every 12 unit out run, the vertical distance need to go down by 1. And so you have a rise, which is negative in this case, so it's go down, and the run is 12 positive, so we go to the right. And if we were to go down 1 more, then we would need to go over 12, and so on. Now, obviously, this is the ramp, not the steps, so it would build to look something like this. In most applications, when we sketch the graph of the function, we only need to use the first quadrant where x is positive and y is positive. This is because the domain of the function is understood positive. Also, we don't have to use the same scale for both x and y axes. This is a linear equation, so we only need 2 points. When x equals 0, f of 0 is 10 minus 1 over 12 times 0, which is 10. And we will pick conveniently when x equals 12. When x equals 12, f of 12 is 10 minus 1 over 12 times 12, which is 9. 1 over 12 times 12 is 1. 10 minus 1 is 9. Now we have 2 points. The first point is x equals 0, y equals 10. And the second point is when x equals 12, y equals 9. We then plot these 2 points on the graph. The y-intercept is 0, 10. And when x equals 12, y equals 9, which is roughly right there. And then we finish this by drawing the line that would go through the graph. Now, this graph doesn't look as good because of the scale. We would have a better looking graph if we were to scale this. Perhaps we would make the scale of the x-axis smaller. But we'll leave it at this. What is the slope of this graph? The slope of the graph is negative 1 over 12. That means for every 12 unit out, we would go down 1 unit. At what rate is the ramp changing? Well, the rate is the slope, so we just simply interpret it. The slope is the rate, so it is the dependent variable y over the independent variable x. The unit for y or the unit for f of x is in inches, and the unit for x is also in inches, but in this case we will not be able to cancel the inches over the inches because this is the unit. We were told that both of these are in inches. we say that the ramp is decreasing because the slope is negative at a rate of 1 inch for every 12 inches run. And so what that means is, again, if we were to go out or run 12 inches, we would need to go down 1 inch. Another way to interpret it is to put it in the unit ratio. And so minus 1 over 12 is negative 0.0833. And the units is again inches over inches. The advantage of putting this in the unit ratio is now we have negative 0.0833 over 1. Again, inches over inches. This means the RAM is decreasing at the rate of 0.0833 inches for every inch out. But the drawback is that we have to work with a decimal number here.